Okay, this question is from one of the slides in our thermodynamics class. A gas of neutral hydrogen atoms in local thermodynamic equilibrium has equal number of atoms in the nth state equal to 1 and the nth state equal to 2. What is the temperature of the gas? This is our Boltzmann equation. And let me just quickly go over what these mean again. Our large N, state 2 in state 1. This is talking about the number of atoms, the quantity of atoms in the particular state. So all we have is neutral hydrogen. So this is literally the number of atoms in state 2. And what is state 2? This is, you have your nucleus. State 1 is when you're n equals 1, it's like your lowest energy level. State 2 is a photon comes in, excites this, and this jumps to its next energy level. So that's a second state of excitation of the atom. And our problem gives us that the number of those atoms are equal to the number of atoms in state 1, which is just state 1 is the lowest energy level. So the number of these two atoms are equal, so it's a 50-50 ratio. That means we have N2 over N1. If they're the same, then this reduces just down to 1. So that's this part of our Boltzmann's equation right here. Now, what is G2 over G1? Okay, looking at G2, let me erase this and let's start somewhere else. Well, this G sub 2 and G sub 1 is talking about our number of degeneracy in the nth state. So for hydrogen, it's 2n squared. This will be our second state, n equals 2, other words. So this is n equals 2 using this equation. And this is n equals 1. So 2n squared. This is going to work out to be, well, 2, 4, 8. This gives us 8. This is 1 squared times 2 gives us 2. So this gives us 4. Okay? That's this part right here. And now we have this whole mess right here to deal with. First, let's set this up. So we know we have 1 from here. Our ratio of number of atoms in different states is equal to 4, our ratio of degeneracies, times e to the negative change in energy divided by Boltzmann's constant, which is just a number, times our temperature, and we are trying to figure out the temperature of this particular gas. So let's just divide this by 4 real fast and get our E term by itself. So we'll have 1/4 is equal to E to the negative change in energy over Boltzmann's constant times the temperature. Okay, at this point, you can raise everything, take the natural log of, let's just call this 0.25, 1/4. And raising this to the natural log, we bring everything down. We have our negative change in energy over Boltzmann's constant times the temperature. Now that we have our temperature outside, or I wouldn't say outside, now that we have our temperature non-exponential, we can switch out our natural log and our temperature. And now that we have solved for temperature, our negative change in energy over Boltzmann's constant, and now we got times natural log of 0.25. Now we need to figure out, well, what is change in energy? This is our negative change in energy. Our change in energy is equal for hydrogen 13.6. It's normally times z squared, where z is the atomic number, but for hydrogen, our atomic number is 1, so 1 squared is still just going to give you 13. But I'll go ahead and include it so we don't forget when we're dealing with other atoms. We have 1 over the nth state initial squared minus 1 over the final state squared. This will give you your results in electron volts. Let's simplify this a little bit. Change in energy is equal to 13.6 times, what is our initial? Well, here's what you want. You want our change in energy to be positive. So what is this in initial? Try to think going from a lower state to a higher state. So if you have your nucleus and you're going from a lower state, our electrons going around here, and say n equals 1 would be our initial state, and it's going to go to a higher state. In other words, it's going to absorb a photon and jump up to this higher state. So our initial is 1. So remember, our initial state was in the ground state. So 1 squared is 1. Minus, well, this part right here, we've jumped up to our new state where n is equal to 2. This first excited state. So 2 squared, this will be 1 over 4. And this will give us our EVs, our electron volts. This is going to work out to be a change in energy is equal to 10.2 electron volts. Well, our Boltzmann constant, it's necessary to have this in joules. So we know that our joules, for every electron volt, we have 1.6 times 10 to the negative 19th joules. So that's our conversion factor. That gives us a change in energy is equal to 1.63 times 10 to the negative 18th joules. So now we can take this and plug it into here. Let me make some more room. So our temperature is going to be equal to the negative change in energy, negative 1.63 times 10 to the negative 18th joules. Let's do our dimensional analysis over here. We got joules. All of this over our Boltzmann's constant. Boltzmann's constant, what is that? Boltzmann's constant is equal to 1.38 times 10 to the negative 23, and that's in joules over kelvins. So if I plug that in here, we got 1.38 times 10 to the negative 23, and that's in joules per Kelvin. And then we have natural log of 0.25, which is a dimensionless parameter. It does not change anything. This is going to give us kelvins for our temperature, so at least we're in the right dimension again. This gives us a grand total at the end of 8.53 times 10 to the 4th kelvins. Now we have calculated the temperature.